All right, and just an addendum to my previous video. The um, at the very end, we had a problem where the logic was kind of negated, and I just made this comment offhandedly about, well, just we'll flip the bits and it'll all be all right. And I wanted to go into more detail as to exactly why, how I know that, and then really what the right way to fix it. So the first thing to notice is on the schematic for the 7-segment display, the MOSFETs here are not N-channel MOSFETs, they're P-channel MOSFETs. And that means that in order for them to be on, this needs to be shorted to ground. And it needs to be 0 volts here. And there's an external pull-up resistor that by default will just pull the voltage up to whatever VCC is. And what happens here is this line will then pass current when this is shorted, and it'll be blocked if it's not. And that's really the source for each of the different cathodes. So that's why we had to put a 0 on just one of these cathodes in order to turn just that one digit on. Over here in the anodes, it's the same thing. If I want to be able to short one of these connections, I need to put a 0 into that particular bit in order to sink current into ground. To turn it off, we need to put a 1 to block, well, we put a 1 to put voltage on here. There wasn't enough voltage drop to let the diode start to conduct, and so the anode was off. All of that being said, that's the wrong way to do it. The right way to do it is to do what we did with the microchip part, which was to go into what's called open drain, where when we are writing a value, we're either sinking ground, or we're sourcing voltage, or we're in high impedance mode. And that would be the most appropriate. When I want to turn this MOSFET off, instead of putting voltage on the line, I really want to be in high impedance mode and let this pull-up resistor do its job. Over here, when I'm in the anode, I don't really want to have to source a voltage here to block this diode. What I really want to do is be in high impedance mode, and then that way no current can flow. So looking back at our Verilog source code, we fixed it here by negating the logic, but really what I want to be able to do is to go in between sinking ground or high impedance. And to do that, I need to change these output wires to be in-out parameters. And then what I need to do is I need to go through here and change, for instance, here's anodes out. There's no built-in way to kind of map these to open drain like we did with the microchip. Like the microchip, we could put the output port into that special mode where we are enabling or disabling the output buffer. There's no built-in way to do that in Verilog. Instead, what I need to do is to go bit by bit and say, for instance here, if anodes of 0 is equal to a 1, then that means we're going to sink to ground. Otherwise, we're in high impedance mode. And theoretically, I could go now and copy this all 9 times and then make another set of copies here for the cathodes. And that's just a little tedious. Instead, what I want to be able to use is this other special feature in Verilog that's called the generate statement. And the generate statement allows me to generate multiple statements, substituting a variable for some value in the statement. So this is kind of going to look like a for loop, but it's actually going to be generating code at compile time. So this makes more sense here once I paste this value in. So let's come here and say, for example, genvar, we'll call it bit. And we're going to start off here with bit is equal to 0. And while bit is less than, our limit here is going to be 9. Bit is equal to bit plus 1. We'll give a label here for assign anodes. And now what I can do is move this line into my generate statement and substitute here this 0 for bit. And unlike, like say, C language, where this would just be a sequential loop, what's really going to happen is you can imagine this is going to be replaced by the 9 assignment statements that I would have to copy and paste manually. So this is just a way to generate these to be without having to do the copy and paste and then risk having errors crop up from copy and pasted code. I can then reuse that same structure here and in this case we're going to go to 5 well, we do less than or equal to. It might be more consistent that way. All right, and then this would be cathodes out, and then cathodes, and then we can delete this. So now, whenever I write a 1 in the anodes bit, that's going to sync to ground, and it's going to allow that anode to be on. Otherwise, if it's a 0, we're going to be in high impedance mode. The same is true now for our cathodes. Our cathodes, if I put a 1, I will write a 0, I'll sync to ground, and that will activate that P-type MOSFET. Otherwise, we'll be in high impedance mode, and then this pull-up resistor will do its job. So with that being the case, this will accurately fix the problem that we had with that kind of negated logic. There is just one more problem that we have to address, and that is in the constraints. The constraints file, we call these ports input and output ports. We really should take a look at the implementation and just make sure that nothing has changed in there. But that'll take care of it. This will do everything that the other version did. I will post an updated version of this to the website. Hope this was helpful. Hope this explains a little bit better how we use in-out ports. And catch you with the next video.